Now let's learn about the background of conventional digital locks. With the emergence of smart home technology, ordinary homes have transformed into highly automated living spaces. Digital door locks are currently an ever-growing trend in Singapore, particularly in HDBs, as it offers unparalleled convenience, security, and remote access control. However, users are still required to manually move the door, which can be too heavy and dangerous for elderly with mobility impairments to do so. Due to their limited range of movement, disabled elderly may also find it difficult to reach out to access the digital lock. Moving on with our problem statement. Since the introduction of smart home systems, digital door locks have been a popular smart home appliance. However, conventional digital door locks do not adequately address the needs of elderly individuals with physical disabilities. With their limited range of movement, they often struggle to access the digital lock and move the door. Therefore, there is a need to develop an accessible and user-friendly automatic door and lock system for elderly with mobility impairments. Our proposed solution addresses the inconvenience faced by people with disabilities when navigating doorways. The smart door activation system integrates touch sensors, internet connectivity, and user notifications to provide seamless access to doorways. Users can activate doors with a simple touch, control them remotely via smartphone or other devices, and receive real-time notifications about door status. First, let us introduce the sound sensor. The sound sensor serves as a critical component in smart door automation, enabling the system to respond to specific sound cues for hands-free door access. Functions of the sound sensor include a trigger mechanism, which detects specific sound patterns, noise level 400 Hz to activate the opening of the door. Hands-free access, which enhances convenience by automating door opening for people with mobility impairment. The RGB indicator is a visual feedback mechanism incorporated into our smart door automation system. Red RGB on indicates sound detected at a frequency below 400 Hz, serving as a warning signal. Green RGB on indicates sound detected at a frequency equal to or greater than 400 Hz, signaling readiness for door activation. For the main board, the sound sensor will provide feedback indicators such as using RGB to indicate the sound detection activity. The green light will blink if the sound detected is higher than 400 Hz, else the red light will be on. For ThingSpeak integration, if the sound more than 400 Hz is detected, the Arduino board will read the signal and it will write using MQTT a signal to the ThingSpeak field, changing the state of the field from 0 to 1. Moving on to our second component, the touch sensor. By incorporating a touch sensor into our smart door system, it would allow users with limited mobility to close the smart door with minimal effort upon entering or leaving the house. The functionalities of the touch sensor are: 1. Ease of usage. It improves accessibility by removing the need for physical door handles, which can be challenging or inaccessible for individuals with mobility issues. 2. Safety. It reduces the risk of falls for individuals who use walking aids, since they do not need to hold the door open and focus on maintaining their balance at the same time. For the RGB indicator, if the touch sensor detects physical touch, the board's built-in RGB will turn green. If the touch sensor does not detect physical touch, the board's built-in RGB will turn red. Whenever a user touches the sensor, it sends a high signal to the MKR board. Following this, the board publishes a 0 to field 1 of our ThingSpeak channel via its ThingSpeak's MQTT broker. The LED serves as a status indicator for the smart door activation system. It has 2 types of blinking to indicate different scenarios for door opening and closing respectively. The LED functions such that when the sound sensor is on, the field 1's value of ThingSpeak becomes 1, the LED will turn on for 5 seconds to indicate door opening. When the touch sensor is on, the field 1's value of ThingSpeak becomes 0, the LED will blink every 0.2 seconds to indicate the door closing. For the RGB indicator, when the field 1 value is 1, the RGB turns green. When the field 1 value is 0, the RGB turns red. Next is our fourth component, the servo motor. The servo motor serves as an essential part of smart door automation, as it allows the door to be opened and closed without the need for physical force from the user, allowing for a more accessible system. Its functionalities are: 1. Activation. It reads the field data from ThingSpeak to determine if the door should be opened or closed based on predetermined values. 2. Enhanced accessibility. It enables hands-free operation, making the door more accessible for individuals with disabilities, limited mobility, or carrying packages. RGB indication is set to be red RGB on for door closing and closed, and green RGB on for door opening and opened. For the integration with ThingSpeak, the board reads the field data of field 1 of the channel. If the field state is 1 and the previous state is 0, the servo motor is activated and the door is opened. If the field state is 0 and the previous state is 1, the servo motor is activated and the door is closed. If the current field state matches the previous field state, the servo motor remains stationary, preventing the door from moving. Next is our fifth component, the push button. Its purpose is to monitor the state of the door and trigger other components. the push button sends a signal to the Arduino board, which then sends a signal to the ThingSpeak Field 2. For security, it provides authentication and alert user that the door is not properly closed through the app. For the RGB indication, when it is pressed, RGB turns into green and a high signal will be sent to Field 2, which will publish a message to LCD that the door is open. When released, RGB turns into red and a low signal is sent to the LCD that the door is now closed. Moving on, our sixth component is LCD. Its purpose is to display messages to remind users of the state of the door, which indicates the changes of the door status. Its functionalities are 1. Safety management, inform users about door status. 2. Signaling purpose, to remind users to close the door when necessary. The RGB indicator for this component is set to be red when the door is open and green when the door is closed. For the integration of ThingSpeak, when the push button is activated, Field 2 will then be 1, which will then trigger the LCD to display a message, close the door. When the push button is deactivated, Field 2 will then be 0, which will then trigger the LCD to display a message, door close. For remote access, we utilized a IIoT MQTT panel mobile app. By utilizing a MQTT-compatible IoT dashboard mobile app, users gain the ability to remotely control their door from any location using 2 buttons. The app is also designed to show the 2 fields to monitor the status of the door.
Please let me in. I want to go home now.
Our key innovations in this project are: 1. Using MQTT to interconnect multiple sensors and actuators. 2. Automatic door activation. 3. Physical sensors and remote app control of door. 4. Able to collect and analyze data in real time. This slide outlines the challenges encountered during the project and the corresponding solutions implemented to address them. Challenge 1 is data collision on ThingSpeak. Multiple components writing data simultaneously may cause interference. The solution is to implement MQTT protocol as it enables asynchronous data transmission. Challenge 2 is high sensitivity of sound sensor. It detects even the slightest sounds, leading to frequent false positives. Our solution is to adjust the threshold to filter out low-intensity sound. This slide highlights future work recommendations to address security concerns and enhance accessibility in the smart door automation system. Our first recommendation is randomized sound patterns for authentication, so that it generates unique sound patterns for each authentication attempt. This is to tackle the issue of unauthorized access due to overheard passwords. Our second recommendation is implementing customizable user interface to personalize for diverse accessibility needs. This is because our UI currently is designed for the general disabled community.